Hi everyone, I'm Jaiji Li. I'm postdoc at MIT CSAIL HCI engineering group following Professor Stephanie Mueller. And my personal research interest is 3D printing dynamic mechanisms. The project I recently published is about a cable-driven mechanism. So if you try to assemble a cable-driven mechanism like an end effector, it's kind of hard. You have to thread tons of cables inside it through lots of holes, and you have to attach them with a specific tension. So what I do is I 3D print all this geometry just by one step. So this is a print just came off the 3D printer, and you can actuate it like a real tendon. Tendons could conduct force from a certain distance. So if you have a motor here, let's say you have a motor in the middle of the object, it would be huge and make it really heavy. But the tendons could conduct this force from pretty far away position. You can conduct force from here to all the way to the end effector, which when you're pulling it, it would be perform something like pretty magical movement. So that's kind of the things. And also the motion is precise and real time. So whenever I pull it, the end effector would move immediately with my pulling. So this is kind of the most appealing part of the cable-driven mechanism. This kind of mechanism inspired me because cable-driven is kind of most real-time and precise mechanisms in our body. So if you look at our finger, a tendon which is actuated with muscle here, and it's going all the way through the finger, and once you pull the tendons, it precise a real-time and precise motion to the fingertip. It does not need a series of actuators one by one, but it's just connected to the end effector and actuator directly. So also in robotic, people using this kind of mechanism to conduct this very precise motions. So I'm kind of repeat this work, but with saving more human labor and manufacture time with 3D printing. We have a design tool which have a very simple logic of how to embed those cables into a geometry. So you can input any kind of geometry, you can input a laser-like shape, and the design tool would kind of embed those primitives inside it. Those primitives including bending or coiling or twisting. The reason why this method is important is if you try to assemble a cable-driven mechanism by yourself, you would have a lot of problems and challenges with it. First of all, you have 3 of tendons in it, and you have to thread hundreds of holes. And also you have to adjust the tension of each. If you look at our fingers, our fingers are of varying tensions, so when you grab, it's like a fist. But if the tensions are unbalanced, you will have something like this. Of course, it's also my hobby. I was an undergrad with major of architecture, and at that time I used a lot of 3D printing to do static models and also some assembled models with lot of parts. I'm a big fan of 3D printing. Yeah, the reason why I have lots of passions on my research is actually I can see my objects actually evolve. Each time I redesign and reprinting my objects, we can see they become smarter and more sophisticated and more dynamic with each iteration. So the reason why I recommend CSAIL to everyone is because it's a really amazing place. Before coming here, I can't imagine such a place that you just walk on a corridor and you just find people are playing with a robotic dog from Boston Dynamics, or a humanoid robots which really walking along with you. So this is great inspiration that you could kind of impersonal feel all these motions and these mechanisms of robots and how people are developing new technologies to driven them. This is a really great place. You talk to any random people, you will get tons of feedback and see lots of collaboration opportunities. So that's why I love CSAIL, and this is the reason I am here.